Hello and welcome to MT3. Now we are in our final example in series solutions to ordinary differential equations. We're going to look at Hermite's equation. And this is given by y double prime minus 2x y prime plus 2 alpha y is 0, where alpha is a real number. This is the kind of differential equation we need to solve when we are dealing with the quantum harmonic oscillator, and I'll explain in a bit why. So just to look at the people behind what we are looking at now, there's Pierre-Simon Laplace, who first defined the Hermite polynomials, but apparently in a way in which we wouldn't recognize now. So they were rediscovered, understandably, by Charles Hermite. I guess he's French, so Hermite. Oui. Okay, and we're going to see now why this is an important differential equation for us when we are studying, especially when we study quantum mechanics. Okay, so to bring this in a form which links to the quantum harmonic oscillator, we will first make a transformation y is equal to x squared over 2 times u of x. Now I'd like you to show by a standard change of variables. This is an important skill to have when you're dealing with differential equations. So if I change variables from y to u using this transformation, then show that this differential equation becomes this one here, where we have a differential equation in u, where u is a function of x. Alright, so please show that. And we will soon show that the quantum harmonic oscillator, the Schrodinger equation, can be written as psi double prime plus lambda minus z squared times psi 0. I know this doesn't look like the Schrodinger equation, but we'll show that it is in fact after some transformations. So if you compare these two now, you can see that psi is equal to u, psi of, if my variable here is z, you'll see why. So psi of z is u of z, and that would be given in terms of the y's as the inverse transformation. So it will be e to the minus z squared over 2 times y, and these y's are the solutions to the first equation, the Hermite equation. And what we will see is that these solutions will be the Hermite polynomials, defined in minus infinity to plus infinity, with weight functions in the standard sense of the weight functions of the inner product and function spaces of wz is given as e to the minus z squared. Okay, this is where we are going. So let's start with the quantum harmonic oscillator. The Hamiltonian is given as by a kinetic energy part and a potential energy part, so it's h is equal to minus h bar over 2m d squared by dx squared plus a half kx squared. K is your spring constant, and we know from our classical harmonic oscillator that k is related to the frequency through omega is equal to root k over m, so k is equal to mass times omega squared, and let's use this expression for k. So we can now write down our Schrodinger equation. H psi is equal to E psi, and this means we have minus h bar squared over 2m psi double prime plus a half m omega squared x squared psi is equal to E psi. Let's divide off by this constant term in front of the psi double prime. So we have psi double prime plus in brackets 2m e over h bar squared minus m squared omega squared over h bar squared times x squared, close brackets, psi is equal to 0. Now we're going to do something called coordinate scaling. So we're going to define a new variable z. This is why we had a z in our equation earlier. And z is related to x. It's not the z dimension, it's just a new variable z related to x by a constant alpha. I don't know what alpha is at present. We'll choose alpha soon. So we change variables. D by dx is equal to dz by dx, d by dz. But dz by dx is simply alpha. That's equal to alpha d by dz. D squared by dx squared, you do it the same way, you will get alpha squared d squared by dz squared. So now we can change variables everywhere. So psi here is a function of x. We're now going to write it as a function of z. And the second derivative with respect to x will be written in terms of something with respect to z. So with that transformation, the quantum harmonic oscillator is not the simple harmonic oscillator. The quantum, oops, wrong kind of pen. The quantum harmonic oscillator becomes alpha squared times d squared by dz squared of psi of z. I put the z there to remind us that now it's a function of z. And then we have the stuff in the parenthesis times psi of z is 0. Now what we're going to do is divide by alpha squared, because I want to keep this first term not having any, the first term I wanted to have a coefficient of 1. So we divide by alpha squared throughout, we get this equation. Now we're going to choose alpha such that the second of these terms, the thing in the red box, is 1. That means alpha is the square root of m omega over h bar. Now with that definition of alpha, the first term in the parenthesis, which involves the energy, it becomes 2m e over h bar squared alpha squared, which after some manipulation is written as e over e naught, where e naught is a half h bar omega. You should start saying, this is looking interesting now. So what we're going to do effectively is replace this first term, which is e over e naught. It's a scaled energy, right? I mean, you can define it as epsilon, which is e over e naught. And if we effectively what we are doing is, if we agree to measure our energy in units of h bar, half h bar omega, then we get some dimensionless quantity here. And what we have done, by the way, is make every quantity dimensionless. Epsilon has no dimensions. It's an energy divided by an energy. It's dimensionless. You can convince yourself that alpha given here has the dimensions of 1 over length. Try it out. And what we do then is so if we have alpha as having the dimensions of 1 over length, what it means then is that z, which is equal to alpha times x, has the dimensions, well, it has no dimensions. X has the dimensions of length, alpha has the dimensions of 1 over length, z has no dimensions. And what we have done is we've written the quantum harmonic oscillator Schrodinger equation in a dimensionless way. And in doing that, we have already recovered the standard energy units of the harmonic oscillator, and we already have the half h bar omega in there. So psi double prime of z plus, in brackets, epsilon minus z squared, close brackets, psi of z is 0. That's our quantum harmonic oscillator in these scaled dimension-free coordinates. Okay, and now we can make our comparisons of this equation, call it B, with the equation A, which is on the previous page. Here it is. And you can see that psi is u of x, epsilon is 2 alpha plus 1, and z is x. Sorry, I had the equation A wrongly labeled here. It's not this one, it's this one. Okay. Now, I hope you've been able to notice something interesting already, that epsilon, which is E divided by E naught, is equal to 2 alpha plus 1 when we map A onto B. That means our energy is given by h bar omega alpha plus a half. And it looks like it's exactly in the form of the energy of the states in a simple harmonic oscillator. But we haven't actually solved anything as yet. But before you get too excited, well, we haven't yet decided that alpha is an integer. At this point, alpha is a real number. So this is not the energy of the simple harmonic oscillator, but it's tantalizingly close to it. If we can show that alpha has to be an integer, then this will be the energy of the nth state, of the alpha state of the simple harmonic oscillator, of the quantum harmonic oscillator, right? But you can see where things are heading, and we are already getting key concepts in the quantum harmonic oscillator without actually having solved anything. Dimension analysis has given us quite a lot of this, and that's a great technique. So coordinate scaling is the method we have used here to convert our physical Schrodinger equation into a dimensionless equation, which we are going to solve. And we've already got the fundamental energy scale, we've got the fundamental length scale, And we need to show that alpha is an integer. We haven't yet shown that. And when we do show that, we will have the energies of the states of the quantum harmonic oscillator. And we've done this without solving any odd differential equation. Now, something similar can be done for the hydrogen atom. You can perform coordinate scaling on the Schrodinger equation for the hydrogen atom, and you will find the Bohr radius and the energy of the ground state of hydrogen from there without actually solving anything. It's kind of cool to see it. Yeah, it's a powerful technique which is used in quite a number of branches of physics and engineering. So back to the Hermite equation. This is the one we need to solve before we can put the Hermite solutions into the solution for the Schrodinger equation. So y double prime minus 2x y prime plus 2 alpha y is 0. That's our equation. We're going to use the method of Frobenius. So y is expanded as x to the k times a power series, and as usual a naught is not 0. We need to find the singular points. Well, there are no finite singular points. If you look here, I mean, it's already in the standard form, so p of x is minus 2x. It's well behaved for all x except x going to infinity, and q of x is well behaved. It's just a constant. So there are no finite singular points. If there are, I can't remember if there are infinite singular points. I haven't worked it out, but just look at Arfkin's book or Riley's book and you will find there's a table somewhere which tells you about the infinite singular points. Okay, now I'd like you to show using the standard methods. I haven't done it here. We haven't gone through the steps here. That's we get a recurrence relation. It's given here, which relates an plus 2 to an. And the smallest n, when we do this, our sums will go from minus 2 to infinity. So the smallest n is equal to minus 2. And as usual, we impose conditions that a of minus 2 is 0, and so is a of minus 1. Now this is something you do need to show, so please show this. It's very important. Yep. Now to get the indicial equation, what you do is you choose the smallest value of n, which is minus 2. Put it into the recurrence relation, use the fact that a of minus 2 is 0, so this term will be 0. And then you get an expression for a naught. A naught times k minus 1 is 0. Now since a naught is not 0, that means k times k minus 1 is 0. That is the indicial equation, and that can be solved to give us two values of k, 0 and 1. Now from Fuchs' theorem, we have definitely one solution with k is equal to 1. That's the larger of the roots. And maybe one with k is equal to 0. We don't know. There's another negative value of n. Let's have a look at it. If n is equal to minus 1, you will get a of 1 here. And here we'll have a of minus 1. Now a of minus 1 is again 0 by our requirements. So we have then an expression for a of 1 times k plus 1 times k is 0. Now for k is equal to 0, there's no condition. For k is equal to 0, this term is 0, so there's no condition on a1. It could be anything. But we may choose a1 is 0. This is our choice. And for k is equal to 1, k plus 1 times k is non-zero, therefore a1 must be 0. There's no choice here. Now you may ask, in this particular case, okay, so here that's fine. You know, if k is 1, then a1 must be 0. But if k is 0, what if I didn't choose a1 as 0? Somebody once asked me this a few years ago. But what happens is, if you don't choose a1 as 0, you will end up with a linear combination of solutions. One which depends on a0 and the other which depends on a1. It just makes your life complicated, but you get nothing new. Now it's worth trying it for something. So go ahead. Choose a1 as non-zero and see what you get. Yeah. Let's now what we're going to do for the remainder of this analysis is we're going to make a1 0. So we have two recursive relations, one for k is equal to 1 and the other for k is equal to 0, and I've written them down here as a and b. An observation, a couple of observations before we go on. If alpha is a positive integer, then both a and b will lead to terminating series. Can you see why? So if alpha is a positive integer, then there, here and here, then there will be n equals to alpha such that we have a 0 in the numerator, so there will be no further a coefficients a. They will all be 0 once n is equal to alpha, or in this case n plus 1 is equal to alpha. Yes, so the series will terminate if alpha is a positive integer, and these, as we will see, will lead to the Hermite polynomials. For all other values of alpha, we will get an infinite series. It will be non-terminating. So let's do this case by case. Case 1, we will choose alpha to be a positive integer. Let's choose alpha to be 0. So let's take the case k is equal to 0. If k is equal to 0, we are dealing with this recursive relation, and now we've got alpha is 0, so there's an n minus 0 in the numerator. And the very first thing you do is you put n is equal to 0 in this recursive relation. So that relates a0 to a2. But if you put n is equal to 0 in the numerator, we'll have 0 minus 0, which is 0. So a2 is 0. And for this case, we will have a terminating series with only one term, a0. I put down here, this is an even power of x, isn't it? Because this is x to the naught. Yeah. It's a terminating series. Now if k is 1, then we have this recursive relation, sorry, this one here, if k is 1. Now remember, alpha is 0, so we have a 0 here. And then we have a n plus 2 is equal to 2 times n plus 1, but this n plus 1 will cancel with the n plus 1 in the denominator. So a n plus 2 is just 2 a n divided by n plus 2. I've written that down here. So we have a simpler recursive relation. A n plus 2 is equal to 2 times a n divided by n plus 2. Start with a0. N is equal to 2 gives you a2. a2 is equal to 2a0 divided by 2. N is equal to 0 gives you a2. N is equal to 2 gives you a4. a4 is equal to 2a2 divided by 4. And you can put in this value for a2. That gives you 2 squared a0 divided by 4 times 2. N is equal to 4 gives us a6 as 2 cubed a0 divided by 6 times 4 times 2. And in general, there's a pattern here. A of 2m, where n is 2m, is equal to a0 divided by m factorial. So this gives us a power series. What have we got here? We've got y is equal to x to the power of 1, and then we've got the sum m goes from, m is now any integer, positive, m goes from 0 positive integer, from 0 to infinity of a 2m x to the 2m. Only even terms are in here because all the odd terms are 0. Why the odd term 0? Because we don't, if you put, we chose a1 to be 0, so there are no, and it's a1 which generates all the odd terms, so there are no odd terms in this series. And we have this power series. Now this looks suspiciously like the sign expansion, except it isn't, because we have only positive terms here. There's no sign. The sign expansion has positive and negative terms alternating. It looks like this will diverge as x tends to infinity. It's non-terminating. It has odd powers of x. Alright, then we choose alpha is equal to 1, and we do the same. For k is equal to 0, we have a recursive relation a n plus 2 is equal to 2 times n minus 1 divided by n plus 1 times n plus 2 times n plus 1, and the whole thing times a n. In the same kind of way, I'm not going to bore you with this, you form each successive term in the series, and you end up with a non-terminating series in this case. So y of x is equal to a0 times 1 minus x squared minus x to the 4 minus x to the 6, and you've got terms in the denominators. This is again non-terminating even powers, and again it looks like it's diverging. Why do I say that? Because we're getting the same sign in each term except for the first, and they have larger and larger powers of x. So as x goes to infinity, it's quite likely this will diverge. For k is equal to 1, we have a terminating series this time, because we have a recursive relation which is a n plus 2 is equal to 2n a n divided by the stuff. And once you set n, you start with A naught. Once you set n is equal to 2, so let's put this here. So n is equal to 0. We get A2 is 0 and all subsequent terms are 0. This is the terminating series, which is given by yn is equal to x to the 1, k is 1, that's where the 1 comes from, times A naught. And here we have got odd powers of x. And in the same way, you can go on for alpha as 2. You will have an even series. I've now labeled them as an even series and an odd series according to the powers of x. The even series will be a terminating one, a naught times 1 minus 2x squared, and the odd one in this case is non-terminating. Yeah. Now if you collect all the terminating series, these are polynomials and these are the Hermite polynomials. In their standard conventional form, they are defined to be h naught of x is 1, h1 of x is 2x, h2 of x is 4x squared minus 2, etc. This is given in Riley, Hobson and Benz 18.9. Now if you compare these series with what we've got here, let's have a look. We had our first series here, so this would be, this is equal to a naught times h naught of x. Then where's our next terminating series? That's here, and this is equal to a naught times h1 of x. I think I missed something. H1 is 2x, so it's a factor of 2 here, which is what we need. It's a naught over 2 times h1 of x. A naught over 2 is another constant. It doesn't matter if it's a naught or a naught over 2. And for alpha is equal to 2, we get, let's see what this one is. H2 is defined to be 4x squared minus 2. So this thing is equal to minus a naught over 2 times h2 of x. Okay, so our terminating series are then proportional to these Hermite polynomials. And these are the ones which give us our which are used in the solutions of the simple harmonic of the quantum harmonic oscillator. So to get these Hermite polynomials, alpha must be a positive integer including 0, and in which case our energy states are given by h bar omega times n plus a half, where n is 0, 1, 2, etc. So what about the non-terminating solutions? Because, you know, these non-terminating solutions are also solutions to the Hermite equation. So what about them? Why don't we use those? Why does the quantum harmonic oscillator use only the Hermite polynomials in them? Well, the answer here, and I'm not going to show it to you, but if you did want to see it, I can kind of give you a proof in class, is that those non-terminating series can be shown to have an asymptotic form of e to the x squared. Now remember, our wave function psi is given as e to the minus x squared over 2 times y of x, where y is the solutions to the Hermite equation. Well, now if y goes as e to the x squared, then psi will go as e to the minus x squared over 2 times e to the x squared, which is e to the x squared over 2. Now this is not normalizable in minus infinity to infinity. And therefore, on the basis of physical grounds, we don't see these solutions. These non-terminating solutions are not physical wave functions. They're not related to physical wave functions. Therefore, we don't use them in as solutions of the quantum harmonic oscillator. All right, so that's our series solution treatment of the Hermite's equation. I hope you have understood how the Hermite's equation relates to the quantum harmonic oscillator, and we showed this using a transformation of variables and dimensionally scaling the quantum harmonic oscillator to make it dimension free, and that let us not only discover the physical energy scale, the physical length scale, but it also let us show that the energy of the system is given as h bar omega times alpha plus a half, which is exactly what is the case when you solve the Schrodinger equation. But we got this without solving the Schrodinger equation, and that's pretty neat. All right, thanks for watching. All the best.